Okay, so welcome to Lecture 7, Fanno and Rayleigh Flows. Let's just have a kind of recap where we are at the moment. So we're looking at duct flows, so flows that have possible variation in cross-section area, and a couple of things that are quite important here. One are area changes, and the other one is that you might be putting heat in, or indeed taking it out, or there might be some kind of reaction going on, like combustion. Very long pipes, we've got the possibility of drag. So when there are changes in cross-section area, usually, well, not usually, this can be dealt with an isentropic approximation. When there are friction is important, then momentum is not conserved, so we need to take into account the fact that some momentum flux pressure is changing with distance. It's called a Fanno flow, and when there's heat is important, momentum is conserved but energy is not, so we need to take that into account in the conservation energy. And this is a Rayleigh flow. So Fanno flow, we look at conservation of mass, energy and state. Rayleigh flow, conservation of mass, momentum and state, mass, energy, state. So that's what we're going to look at today. We're going to look at parts B and C. Just to review the context where we are, we kind of had this story of a supersonic jet engine. We discussed the inlet, geometry of the inlet, this idea that we need to convert the supersonic flow into subsonic flow through compression, presence of a normal shock. We discussed the geometrical changes or the significance of matching the inlet Mach number to the upstream Mach number to the geometry of the problem, and why in many cases this geometry needs to change as the upstream Mach number changes. Lectures 6 we did changing cross-section area. Lecture 7 we're looking at heat being added and removed and effect of friction, which is our lecture 7 today. And what we're going to do in next week is going to look at outlet flows. Now, one of the things that was quite important when we were discussing flowing ducts, lecture 6, was this idea of critical values. The reference state in this is a value of when the Mach number is 1, and contrasts with the case of when we were looking at normal and oblique shocks, where we're using the stagnation reference value for the temperature. Let's just remind ourselves that the stagnation temperature is a conserved quantity. When flow is adiabatic, no heat's being added, no flow does no work. Stagnation pressure is not a conserved quantity. The ratio of stagnation pressure to stagnation density is a conserved quantity, but the stagnation pressure and stagnation density are not conserved quantities. And they are useful as an indication of the potential of the flow to do work. So that's why we calculate those, and that's why we need to go for a series of oblique compressions in order that the loss of stagnation pressure is greatly reduced. Two approaches that we applied, we discussed in the last lecture, of trying to analyse these class of problems in duct flows. Basically a differential approach of trying to relate the change in Mach number to a change in either distance, change in area, or we're going to look at change in the stagnation temperature, or an integral approach, which is to basically literally relate one state to another through a conservation principle. And so what we're going to see is that because of complexity for Fanno flows, we're going to be looking at a differential approach, and there is a way of looking at Rayleigh flows using an integral approach, but we're going to look at a differential approach and make use of some of this. So we're going to really be focusing on this today. Yeah, just to recap from last lecture, the three cases of duct flows simply described as this where we've got changes in cross-section area. We've had three cases: case A, case B, case C. Case A, we said which is easy, that the flow is subsonic everywhere, and the important point there is the exit pressure matches the back pressure. Case C is the other easy case, so these two are easy. And this is a case where the flow goes from subsonic to supersonic, and the flow is independent of the back pressure. The back pressure being low enough that the flow in the contracting and expanding regions fits with the isentropic approximation. So that's the simplest case. The only problem here is that the back pressure doesn't necessarily equal to the exit pressure or design pressure. Case B, slightly more complicated, is a case where the flow becomes choked. Yeah, so we've got Mach number 1 at the choke point, and the flow does follow the supersonic branch after that, but jumps through the presence of a normal shock onto the subsonic branch where it matches the back pressure. So in this case, exit pressure equals back pressure, Mach number is 1 at the throat, and there's a normal shock to kind of match the exit pressure so the back pressure and the exit pressure are equal to one another. Now, in this particular case, just to remind ourselves, for this particular case, A star is equal to the throat area. So A star is a critical critical area associated with the Mach number being unity. So because the flow is choked, then in this region, A star is going to be AT. Case B has got two solutions. Solution 1 in region 1 and solution in region 2. In region 1, the critical area is equal to the throat area because the flow is choked. But when we go on to solution 2 or region 2, then A star doesn't equal the throat area, and we need a little bit of work. And same here, because the flow is not choked, the critical area is not equal to the throat area. So duct analysis, what we're probably going to see as we'll carry on our work, is that we're going to be trying to relate the changes in M, actually the changes in M squared, to changes in stagnation temperature and the changes in and the influence of friction on the flow itself. This will, as we always look at differential changes, we're going to see that this is going to really be changes in M squared over M squared, differential changes over M squared. In terms of fractional changes in stagnation temperature and the effect of friction non-dimensionalized with F dx over d, dx being distance along the pipe. So the first thing we're going to do is Fanno flows, and we're just going to ask this little simple question: is how does the flow change for something with uniform cross-section area as we go from region 1 to 2, and we have a friction applied by the wall. Very, very important in long pipes, gas pipes for instance, and compressibility does have an influence here. So the aim is to relate what is going on in region 2 at point 2 to what is going on at point 1. Now the first thing we do, we're going to be talking about friction, and we just need to overcome a slight difficulty in terms of notation. Well, not notation in terms of terminology. So if you're talking from a kind of fluids community where I kind of sit, then we tend to talk about in terms of friction factors, and there different communities describe friction factors in a different way. So the way we normally take it in the fluid community is that we take the friction factor to be the tangential shear stress to be proportional to half rho u squared. This will be a measure, if you like, of the what do you call it, of an indication of the static pressure in an incompressible flow. And F is this dimensionless friction factor, which is an indication of essentially the drag on the wall itself. It's empirical. Actually, there is a laminar approximation that you can calculate that you've done in year 1. You've looked at the drag on a viscous flow in a pipe, And when we're looking at turbulent flow, can't quite see the numbers here, but this is the Reynolds number associated with flow in the pipe, usually UD over kinematic viscosity. So the friction factor has usually an inverse relationship with Reynolds number for low Reynolds number, with viscosity dominated, and for high Reynolds number, it's usually a constant. This has a dependence on the roughness, and so as the roughness decreases, then the friction factor decreases. That's the usual way of doing it, but there are other ways of doing it. So there are two ways of representing friction factors. One is, as I said before, using we usually call it the Fanning. Well, it's the Fanning friction factor. Used more in compressible fluid mechanics, used in more hardcore fluid mechanics, and used a lot more in civil engineering because they tend to deal with open problems. The Darcy friction factor is used quite a lot in pipe flows, and so American fluid mechanics, they tend to use Moody charts and all these kind of things. And so because of the way the friction is characterized in terms of cross-section area and perimeter of the pipe. So so you will see a difference if you look into books about whether you're using the Darcy friction factor or Fanning's friction factor, but we use a Fanning friction factor. Kind of fits a little bit more with fluid mechanics community. Now, if we're looking at flow in a pipe, as we said before, energy is conserved, mass is conserved, and we now need to look at how the momentum changes with distance. So normally, in the absence of friction, we kind of got our usual thing is the increase in momentum flux is equal to the decrease in pressure, or essentially rho u squared plus b is a constant. Now, of course, this is without friction. And so if we're looking at how friction changes, then we're really trying to look at how parts of this decrease due to the effect of friction on the walls. So ddx will not be a constant when there's friction. So with friction. 0 without friction. It's a little bit more subtle than that because the way that the analysis is derived there are subtleties in the way the changes in area are accounted for or not accounted for. So this is really what we call a long wave approximation. Pipe cross-section areas changing very smoothly with distance. So let's start at the beginning. Conservation of mass. Word equation for this is what goes in goes out, or rho u is a constant. Here we're looking at A is a constant. Cross-section area of the pipe is constant. Conservation of energy, well, what does that really tell us? That tells us that T0, our stagnation temperature, is constant. T0 is T1 plus half gamma minus 1m squared. Conservation of momentum, and so for this we need to look at or appeal to a differential volume for the pipe itself. So take a slice of the pipe, analyse what are the forces on it. So we've got friction around the perimeter. If the width is dx, and the area is A, then the perimeter is going to be pi d, and the area on which the shear stress acts is this, area of element, and we've got tau times this. Now tau is a half f rho u squared times pi d dx. So that's going to be the friction that's being applied, or the drag per unit length applied to the flow itself. So looking at the change in the properties across this pill box, the increase in momentum is balanced by this pressure differential applied to the area, and the sink term due to the friction applied to the perimeter. In addition, we've got the conservation of, we've got the equation of state, P equals rho RT, and the purpose essentially is to find the differential relationship between M and dx. How does that change with distance? So just simplified, this is the defining equations all put together in a more simple form. And really what we're trying to do is trying to convert everything to be a function of m squared in terms of m squared or m, and then we're trying to look at those differential changes. So the momentum flux you saw was in terms of du's, so we convert the du's to du squareds over u squareds using some manipulation, and then we'll convert those to dm squareds over m squareds. So at this stage it's just a little bit of algebra moving around, and yeah, I mean this is just. So what we have here is now, after manipulation, a relationship between dm squared and dx. And so we can comment a little bit more about the type of solutions that may occur. So if the flow upstream is subsonic, so m squared, m squared is less than 1 or m is less than 1, then what we see is that the coefficient, the sign of this term is going to be positive. A positive thing times dm squared must be positive, dx must be bigger than 0. And it tells us if the flow is subsonic, m is going to increase. Of course, it will increase to the only value it can increase to will be the sonic state. Can't increase beyond that, and this puts constraint on the type of solutions that you can have. If the flow is supersonic, we're looking here, supersonic, m is bigger than 1, then we see that this coefficient here, which is negative, times dm squared must be positive, so dm squared must be negative, so m must decrease. So if the flow is supersonic, then the effect of friction is to push it towards a sonic state or a critical flow state. And so we have a similar situation to what we had with the Prandtl-Meyer expansion, is that if we want to find how the flow changes from location 1 to location 2 over a pipe which might have a length LP, then we need to integrate over that distance. So if we integrate between the distance between 0 and a pipe length LP, and the limits are m1, m2, then we can relate, if we know the state of the flow at m1 and we know the length of the pipe, and then we can figure out m2. And of course, as we've seen for Prandtl-Meyer, there's no point kind of tabulating all the solutions for different values of m1 and m2. What we do instead is we use a sonic reference state, a critical flow, critical reference state, and that state obviously is being critical, must be Mach number 1. So what we would do in this particular case is we would have, since the Mach number is going to decrease for a supersonic flow or increase for subsonic flow to a reference state, we take the final reference state, the ultimate one, to be unity. And so what we do is we rearrange this integral so the limit goes between 1 and the Mach number that you're starting with. Actually, what we're doing is we're going from a Mach number of m to a Mach number of 1, which is our reference state. And so that's how we do our calculations. And the solution is plotted in this graphical form in this way. Mach number is along the bottom, and what we have on the vertical axis is 4f times L star. L star is our critical length. It's the distance it takes for the Mach number to become unity, normalized over the pipe diameter. And so if we had a Mach number, let's say 0.7, and we look on this graph, then this would tell us that we probably need a critical distance of 4L star over D is about 0.25 in order for the flow to become, in order to reach a critical state. Let's see how that, just one thing about all of this is that there is a plateau for large Mach number just about above a value of about 1. So for m tends to infinity, Mach number tends to infinity, then the critical length, dimensional critical length is just about above 1. Just one point is that as you probably expect, the flow is being pushed to a state where the entropy is largest, and that occurs when the Mach number is unity. And just one thing is that when we're looking at, so that's being pushed to Mach number unity. So let's look at an example where we've got an initial subsonic inlet. Let's suppose we have a pipe, its length LP, and we ask ourselves, we've got an inlet of Mach number 1, and we ask ourselves, what is the Mach number at this point, M2? We don't know. So what we do is we calculate our critical flow state associated with, and that's the distance it takes for the flow to become unity. So we calculate, we're given this, and we calculate it. Then what we do is we say, okay, so we know that distance. If we work backwards, if we know the distance of L star 1 minus LP, what is the Mach number at that point? So that's how we do it. We start with M1, we calculate L star 1, critical pipe length, we take off the pipe length LP, and then we ask ourselves, or determine by working backwards, what the value of the Mach number is at that point, and that's how we do it. Now, there's obviously a little bit of a problem if the Mach number starts off at 1 and the pipe length is much longer than that distance, and we'll get onto that later. Now, when the flow is supersonic, the distance it takes for the flow to become so supersonic flows in pipes are generated by a larval nozzle, where we say friction is not important. That gives us an inlet in a uniform pipe section of Mach number bigger than 1. But the challenge with supersonic flows is the fact that the distance it takes, or the critical length, the distance it takes for the flow to become sonic, is actually quite short. So if we take a Mach number of 3 and we just simply ask ourselves, over what distance will the flow become sonic, then we find out that's probably about 25 pipe diameters. And so the question is what happens if the pipe's longer? Because obviously it says it's going to get the flow is going to become sonic at one state, and there's no, using this analysis we can't say very much beyond that. Of course, the flow must go through some adjustment, and that adjustment must necessarily be through the formation of a shock, in order that the exit pressure is matched. And so that's what happens, is that as we've dealt with our isentropic analysis for flow through changing cross-section area, where we switch from a supersonic to a subsonic state with the presence of a normal shock, in order that the outlet pressure is matched, then exactly the same happens here. So if the pipe is very short, then the exit flow is going to be supersonic, and we're going to have this kind of simple case C scenario that we've seen for duct flows. But if the pipe is longer, which is typical, then we would end up with a shock formation at a specific point along that pipe, in order that the exit condition is matched. And so what we would end up with is essentially a normal shock somewhere, and we have a normal shock analysis, and we have a Fanno flow over this part, Fanno flow over this part. So we end up with an interesting, complicated solution. So let's do a couple of simple examples. In the first one, we're going to look at flow in a pipe and ask ourselves, if we start off with a pipe with a Mach number of 0.1, remember Mach number goes to, when it's subsonic, it increases up to the sonic case of Mach number 1. And we want to determine the distance it takes for the flow to go from Mach number 0.1 to Mach number 0.5. Second part, if the flow is choked, given an inlet Mach number 0.1, how long is the pipe or the duct? So the first one, for each of the Mach numbers, 0.1 and 0.5, we can determine the critical length it takes for the pipe to become sonic state. So we start off with Mach number 1. L1 is the distance it takes for the Mach number to become unity, and obviously if we have Mach number 2, L2 is the distance for that to become sonic as well. So we calculate those dimensions. Lengths, I have to use the formula because the as we see here, as the Mach number tends to 0, the length has a logarithmic dependence on the Mach number. And so the critical length, dimensionless form, is about 66.92, and for L2 it's about 1.0691. And so the difference between those two lengths, those critical lengths, is the duct length, L1 minus L2. And we can calculate that to be 16 meters. Not a particularly long pipe, but certainly I think it's the same, just a bit shorter than our wave tank downstairs. If we want the flow to go from Mach number 0.1 to 1, or get to the critical flow state, that is actually by definition the critical length of the critical length. So we have our critical length dimensional form 66.92, then we can convert that into meters by timesing by d over 4L. So a distance of 16.7 meters is sufficient for the flow to become choked. Relatively straightforward question. It's subsonic flow all the way through, apart from the last example where it's choked at the exit. Next one's a bit more complicated. I'm going to start off with a supersonic flow, and the pipe length is dimensionless form is 0.9, and we're going to discover when we have a look at the numbers very quickly that the flow, that length is longer than it takes for the flow to become choked. And so, as we've discussed previously, the only way the flow can adapt is that if there's a normal shock that sits somewhere between the inlet and the outlet. And what we're going to find is that the half of the one portion of the flow of the pipe is supersonic, and so the Fanno flow is going to apply on that particular section. Then we're going to match it with a normal shock analysis, and then we're going to have a subsonic or subsonic Fanno flow model. Now the choice of this position is simple, is that you would want that the distance from the normal shock to the outlet is the critical flow, critical distance required for the flow to become choked or reach sonic state. Then we want M relationship between Mach number 2 and 3 to be determined through normal shock analysis, and we want the remaining distance between the inlet and the position of the normal shock sufficient for the Mach number to decrease from 6 to M2. So this has to be solved iteratively. Yeah, so as I say, this is a bit like case 2 in our duct analysis. It's the idea that the Mach number decreases with distance, and it jumps from supersonic to subsonic and then increases up to a case of unity at the outlet. Just imagine what happens if we have part number 6, we increase the pipe length, then of course it will go down maybe to 5 over a very short distance. Make the pipe longer, it goes up to 1.1, make it longer, it goes choked, and beyond that then we need an adjustment, and that adjustment, as I said, becomes through a normal shock. So just in general, the total length of the system must be equal to 9.9, that's what we'll work in, and which means that the first section, the subsonic flow section, plus the critical flow length must be equal to 0.9. And so how do we do that? Well, we kind of guess where what we do is we guess the Mach number at the point at which that transition occurs. That's what we do. We don't guess the distance, we guess the Mach number. Once we guess the Mach number of prior to the normal shock, then that allows us to determine the Mach number afterwards. So we guess this, we determine M3. From M3 we determine the distance it takes for it to become choked. We know the transition distance between M1 and M2, if we know the critical flow length, L2. And so all we're trying to do is for consistency to try to make sure that all those sections add up to the pipe length. Which is how we do it with a calculator analytically. Otherwise it's a kind of an iterative, otherwise we can write a MATLAB script to do this. And that's essentially how we do it. Now remember, across the normal shock, normal shock analysis applies, and we have the explicit relationship between M3 and M2. Remember, this is M3 squared. I always sometimes forget that bit, and so don't forget to take the square root when you're doing your analysis. So the second part of the today's lecture is about Rayleigh flows, and this is a flow in which we add heat. Of course, momentum is conserved, mass is conserved, and we need to take into account the heat that's added in terms of the change in the stagnation temperature. So if the heat added is delta Q, m dot is the mass flux, is the heat capacity, then the heat being added joules per second or watts, we can rearrange this in terms of how the stagnation temperature itself changes due to the addition of heat. So the conservation conditions, mass and momentum and state, and we're going to be using our local stagnation temperature, T1 naught. Now this T1 naught is not a conserved quantity now. That's going to change as we go from state 1 to state 2. So T1 naught, as we explicitly say here, is not a conserved quantity. We can use an integral analysis to try and relate how the flow changes as we add heat. And just to give you a heads up, we're going to be use critical stagnation temperatures, which are going to be conserved in this particular problem. Critical stagnation temperatures, not stagnation temperatures themselves. So we're going to use an integral approach to try and find out what is a conserved quantity as we move along, as we add heat. So conservation momentum gives us the relationship between the ratio of P2 to P1 in terms of Mach number, and we can convert that to determine from conservation of momentum, we can find out the ratio temperature. If we arrange this, we're not using energy in this particular case yet. We can find actually that the product of T1, 1 plus gamma m1 squared, sorry, it's squared here, divided by m1 squared is a constant. And that has no reliance at all on conservation of energy. Now the second useful thing is our relationship between the stagnation temperature and Mach number. And if we combine all of that together, we can eliminate the temperature and find a relationship between T1 naught and Mach number as a constant. And as we've done in the past, that constant can be set as having, which we don't know, we can set this to having a critical value when m1 equals 1. So we can set that constant to be an arbitrary critical stagnation temperature. And what we're really saying is that when we add heat, what we're really saying is that those quantities conserved, that T1 naught is a constant. Now what does change obviously is when you add heat is the stagnation temperature will change. And so this is a way in which we can relate the state of the flow before and after we add heat or take heat away. So we set our arbitrary constant in terms of our T1 naught star. Now T1 naught star is a constant and it's conserved, as in it doesn't matter that heat's being added or taken away. Now the differential approach to this is obviously we're looking at differential changes. So if we start off with our stagnation temperature T naught, sorry, T1 1 plus a half 1 minus 1 m squared. We can convert these to a differential form by taking the log, and then we differentiate. And what we're trying to do is we're trying to determine how our stagnation temperature varies as we change the Mach number. And so we draw on, using this, we draw upon the conservation of momentum, conservation of mass to find our differential relationship between T naught and m squared. And so so we need to put information about how the momentum constraint affects the differential change in T1 in order to determine the differential relationship between the stagnation temperature and the Mach number. And of course, we end up then, as we've had in all of our discussions, the kind of trying to find the relationship between the Mach number and then the key variable that we're trying to measure. We end up trying to take a reference state that we're interested in. So we start off with a stagnation temperature of T naught, the Mach number m. Then we define our limiting state when the Mach number tends to 1 as being our critical flow state. In this case, our critical stagnation temperature. So that's a differential approach. It gives exactly the same as the integral approach. Slightly more complicated to do. And so what do we find? So here is the ratio of the stagnation temperature. So T naught over T naught star versus the Mach number. And as always, we find that if we add heat, add heat means we go in this direction. T naught is going to increase, stagnation temperature is going to increase, we have heat. Then a subsonic flow, the Mach number will increase, and it will increase up to a critical flow state. If the flow is supersonic and we add heat, so we're moving in this direction, then again we're pushed towards the critical flow state. It's worth just pointing out that we have a detonation wave created by a explosive reaction. Then, of course, what we find is that we're adding heat, and we end up with a thermally choked scenario where the flow after the detonation front is actually critical. Now, the main point in these calculations we'll see next bit is that the T1 naught star is the conserved quantity. It's constant and unchanged as we add or take away heat in this problem. So this is just a table referring to what I've just described here. If the flow is subsonic and we add heat, then the Mach number increases because adding heat is this direction up. And if it's supersonic Mach number and we add heat, then the Mach number decreases, pushing towards a sonic flow state. The main point about looking at entropy is that the maximum entropy occurs when the Mach number is 1. And this is actually used when we're looking at detonation fronts. So a number of people have tried to explain detonation fronts in a number of different ways. So I prefer the Rayleigh Flow description, much more intuitive, this idea that you're pushing everything towards Mach number 1, but Chapman describes it into what he says is a in terms of the speed of the flow after the shock, and other people describe it as a state in which the entropy is maximized. They all give the same answer. Let's just look at this example of a flow that's at ambient conditions, well actually 10 degrees centigrade, 100 kPa, inlet Mach number 2.8, so it's supersonic. Heat is transferred from the pipe to the gas, so heat is being added. If we add heat to a supersonic flow, and as we see before, the Mach number decreases, so we're adding heat. Calculate the outlet pressure and temperature, calculate the maximum heat that can be transferred, assuming no shocks per unit mass of the air. So, and the exit pressure and temperature associated with B. So in this particular problem, we're given Mach number 1, Mach number 2, we're given also T1, P1. And we're asked to calculate the pressure after we've added heat, or this change in Mach number, which goes from large supersonic to closer to sonic state. From conservation of momentum, we find that pressure ratio, and we just simply need to substitute in the values on the right hand side and P1 and determine what P2 is. Relatively straightforward. The stagnation temperature prior to heating, T1 naught, is T1 in brackets 1 plus half gamma minus 1, gamma minus 1 m squared, which is 726K, relatively straightforward. Now, if we know the initial Mach number, M1 given, then we can determine by the graph or by substitution what T1 naught over T1 naught star is. Now, if we add heat, then what we find is obviously T naught star, T2 naught star and T1 naught star are the same. It's a conserved quantity. Rayleigh flows. And so, since we know what T1 naught is, stagnation temperature prior to injection of heat, we can determine what the critical stagnation temperature is. And in order to determine how much heat is added, then we need to determine the difference between T1 naught, T2 naught and T1 naught. And since the maximum heat added occurs when Mach number 1, when Mach number 2, M2 is equal to unity, this is a point where T2 naught equals T2 naught star, which is equal to T1 naught star. So since we know that, we can find out how much heat is added, since we now know what T1 naught star is. And if we do that, we can calculate how much heat is added, which is 329 kilojoules per kilogram per second. Now for this state of M2 equals 1, maximum heat being added, then we can determine what the downstream pressure is and the downstream temperature is, since we know what the relationship between T 2 naught, which is T2 1 plus a half gamma minus 1 M2 squared. Now, in the tutorial sheet, and in class tutorial sheet and the problems that we hand out, there's lots of questions, very well explained in the back. There's a combustion question at the end. The general analysis that we've described, where we're looking at changes in cross-sectional area, which we dealt in lecture 6, changes in adding heat in terms of the stagnation, temperature and frictional effects, they can all be added together and essentially combine the analysis by looking at these differential changes. And these coefficients are essentially given in a table of we call influence coefficients, which can allow you to reconstruct a very simple one-dimensional, unsteady description of these complex flow processes that occur in ducts. And these coefficients are given as a table of influence coefficients and can be simply incorporated into a one-dimensional description. And I think there's quite a few MATLAB codes and commercial software, and I think probably ANSYS as 1D pipe version of all of this type of stuff. So very straightforward to include all the influence of area changes, adding heat and friction. So with that, we'll conclude. Thank you very much.